isomers. So let's say I'll just draw some skeletal formulas, and so 1 second. So here are carbon atoms. So then there is an OH, and there's a double bond here. So this one has OH and Cl attached, and so just 1 second for the ozone. So let's start. You have so this one. So we're just going to try and name these two molecules, and that's pretty much it. I'll share a worksheet with this, and we'll move towards isomers. So first thing is, you were supposed to name the molecule in 3 parts or 2 parts. You had a main chain, which was based on the highest presence group. It should be the longest possible carbon atom chain, which should have the maximum groups attached to it, and it should have the maximum double bonds, and it should have the highest presence group. That was what we discussed was going to be the main chain. So longest possible carbon atom chain, which in this case I've marked the main chain. The main chain in this case has 1, 2, 3, 4, and 5 carbon atoms. And because most substituent groups, double bonds, the alcohol and the amines, they're all attached over here. So I've got multiple functional groups. I've got an alcohol and I've got an amine as well. So there is alcohol and there is. Which one has more precedence? What would I call this molecule? Is it pentanol or an amine?
An alcohol.
An alcohol has a higher, has more importance, so it's an alcohol. So it's going to be, the suffix is going to be all for the main chain. And I mean, you have to give the smaller number to the OH group. So which side should I count from? This side, bottom side, or the top side over here? From which side will OH get the smaller number? Or smaller numbers? Altogether, they should get the smaller numbers.
The left side.
Okay, so if you count from the left side, it's 1, 2. This would be the third one. Then you have the fourth, and then you have the. Then you have the fifth carbon atom. So from that side, the OH gets 1, and this OH gets 4. Because if you had counted from this side, this would have got you would have gotten 2 and 5. That would have been bigger numbers for the OH. Remember, the suffix has to be given the smaller number, and it's a diol because there are 2 alcohols, and the positions of both of them is one is at 1 and the other one is at 4. So it's 1,4 diol. The position of the double bond is at 2. And that sums up your main chain. Now what you're going to do is every other thing that's not part of the main chain, that becomes a branch. So you got a 2 carbon atom branch, which is this one. And you've got bromines, and you've got Cls, and you've got an amine as well. All of these would now be connected to the main chain. And they have to be alphabetically named. So I think amine becomes amino. So that would be written first. So you have an amino group. And the next one is bromine. It's good. You have a bromo group, and you have a chloro. And then there's 2 carbon atoms, so that's ethyl. So those are all your branches, and you're going to number them. The chlorine is at 1. The bromine is at 2. The amino group is at position number 5. And you've got your ethyl group, which is at position number 3. So that's going to be the name of the molecule. These are all your branches. Is this clear? This thing?
Yes, sir.
Yes, sir.
Yes.
And we'll quickly do this this next one. The main chain, there's only one main chain in this case, so that's kind of easy. Just one main chain, just 4 carbon atoms. So it's but, and AN, because there's no carbon in carbon double bond. And what would I call it? Would I call it a ketone, or would I call it an alcohol, or would I call it a carboxylic acid? I mean, it's got carboxylic acid, right? So it's going to be
right.
So it's going to be oic acid. And you're going to try and give the carboxylic acid, which is the higher presence, that should be given the smaller number. So you're going to count from this side. So that means the alcohol is now a branch. It's a hydroxy branch. And remember, I told you that the ketone still remains a suffix. I mean, we did discuss over here somewhere. Where's the precedence? Where were the, one second. I said this one. So remember, one very important point is that if you have a carboxylic acid and you've got a ketone as well, I said that when we wrote the presence order, I told you that they always remain a suffix. They would still remain a suffix. So you're going to have 2 suffixes. For the alcohol, it changes. If a higher presence group is present, then they become a branch. They become a hydroxy branch. They become an amino branch. The aldehyde and ketones then never become a branch. They would still be a suffix. So the molecule is going to have 2 suffixes. We said it's oic acid, but it's also a ketone. So the ketone suffix would also be a part of the molecule. So remember this. that even if the name of the molecule or the main suffix is not, I mean, even if there's a carboxylic acid present, there's going to be an additional suffix that's going to be added, and that's going to be the ketone suffix, because that would still remain a suffix. So the molecule would end up having two suffixes. I mean, is this point clear?
Yes, sir.
Okay, so remember, for aldehydes, ketones, and carboxylic acids, even if they're not the highest presence group, they would still be a suffix. And the molecule will then have multiple suffixes. The main one would still be the higher precedence one. The molecule name will still be ending with the carboxylic acid. And for ketone, you would have to give the position. So in this case, it's going to be 3. Okay, this is 3. And the rest are your branches, and there's just one branch, which is hydroxy at position number 2. So that's your only branch. Okay, so this thing, remember this thing. Remember this thing, that ketones, aldehydes, and carboxylic acids, they are always suffixes. So you'll end up having multiple suffixes. So is this clear, this one? Clear, Mikal, is this clear?
Yes.
Yes, it's clear.
Yes.
So we'll just keep on practicing these skeletal formulas, structural formulas, condensed versions, fully displayed formulas. We'll try and name these as we go on. I will send a worksheet for naming that you should try and do. We're now going to try and move towards isomers. We've done all the functional groups. We've done the naming of all the functional groups. Now the next thing is isomers. Now the first thing is, why is isomerism important? Like, why do we study it? Isomer is, I mean, if you know from O levels, it's just a different arrangement of the same atoms. Like if you have a molecule which is C4H10, there are two ways of drawing or two ways of arranging 4 carbons and 10 hydrogens. That's one way, is that 4 carbon atoms are arranged in a straight line. The other one is that the 4 carbon atoms, one of the carbon atom is branched, and you can add in all the hydrogens. There would be 3. Just remember, these are hydrogens. You can add in the hydrogen atoms yourselves. So those are your hydrogens. This one will have 1, 2, 3. One here, 1, 2, 3 hydrogens, and 1, 2, 3. So anyways, so why is that important? Why do we study that? The reason we study that is that it's very helpful in analytical chemistry, that the very first information you get about a molecule, like if somebody discovers a virus, the very first information that they're probably going to get about the molecule is that you can't take the picture of a molecule. Like all these pictures that you see of molecules, they are basically guesswork. What happens is the most probable information that you get about a molecule is the number of atoms that it has, 4 carbon atoms and 10 hydrogen atoms. So what you're going to do is you're going to try and guess what the structure is. What you're going to try and do is you're going to guess that there are 2 ways of drawing this structure. So the molecule C4H10 probably has 2 different arrangements. Then you're going to try and figure out which arrangement is the correct one. This molecule might have different properties compared to this one. So you're going to test that using chemical reactions, checking out the physical properties, and then using analysis, you will probably guess that probably this is the correct structure. So for more complicated molecules, the number of possible arrangements would be many. Like it's going to exponentially grow. As the number of atoms grow, as the number of atoms in a molecule they become more. The number of possible structures that the molecule can have could be many. So this is how chemists basically do this guesswork, that they make isomers. That's the first thing that they do. If somebody discovers a coronavirus, the first information would be the number of atoms it has, or the number of groups, small, tiny groups it has. And then they'll try to figure out like how many different arrangements. It's probably done with a computer because there's so many arrangements, and they'll try to figure out and match the properties and the physical and chemical properties with the structure, and then they'll figure out that maybe this is the correct structure. Is this idea clear why isomers are important?
Yes, sir.
Yes.
Yeah, so they're extremely important in analytical chemistry because that's how you do the guesswork. Now there are going to be two types of isomers. The first one is your O levels isomer. That's your structural isomer. Now a structural isomer is what you did in O levels. The ones that I just drew, those are structural isomers. So structural isomers are that you have the same, it's molecules having the same molecular formula. Having same molecular formula, but different. Structural formula. When I say that they have different structural formula, what that basically means is that the atoms are arranged differently. So the atoms have to be arranged in a different order, different manner. The bonding has to be different. It's, I mean, this 4 carbon atoms in a line, now 4 carbon atoms are not in a straight line. So the atoms got to be arranged differently. And then there's another version, which is a stereoisomer. Now, when it comes to stereoisomers, the definition is that it's going to be a different version of the molecule. But the difference is going to be very subtle. The molecules, there would be molecules having the same molecular formula, and their structural formula would be the same as well. So everything would be exactly the same. So the molecules having same molecular formula. And they will also have the same structural formula. Even the connections would be exactly similar. As the same molecule, same structural formula, but different 3-dimensional they would have a different shape, 3-dimensional shape, and orientation of bonds in space. So basically, they would be connected in exactly the same way, but they would look different. Their shape is going to be different. They will even have the same structural formula. Even the connections would be the same. And the prime example from the real world is like your two hands. Like your two hands are connected in exactly the same way, except they're not exactly the same. Like if you put your two hands on the table, your thumbs are pointing in the opposite direction. The fingers are pointing in the same direction, but the thumbs are pointing in the opposite direction. So that means the shape is kind of different. It's even the connections are same. They're basically mirrored versions of each other. So that's what a stereoisomer is. The molecule would look exactly the same. You would hardly notice any difference, except that there would be a major difference. Like if there's a glove in which your left hand can fit, your right hand will not be able to fit in that glove because your thumbs are pointing in the opposite direction. So is the idea clear? What's a stereoisomer and what's a structural isomer?
Yes.
Okay, so remember, structural isomers, you change the way they're bonded. You change the arrangement of the atoms. Stereoisomers, you don't do that. It's just that the shape or the three-dimensional shape of the molecule is different, even though the connections would be exactly the same. Like, I mean, for example, these are not forming stereoisomers, but you have this molecule, it's going to look, the three-dimensional shape would look different. And so we're going to first discuss structural isomers. And there are three different versions of structural isomers. You've got A, number one. Number one is, this is known as a chain isomer. And they're going to be very specific. They might ask you to draw a very specific type of structural isomer. So a chain isomer is you change the arrangement of the carbon chain. So you've got one molecule, let's say having 5 carbon atoms, right? In a straight line. I'm ignoring all the hydrogens right now, just focusing on the carbon chain. So there are 5 carbons in a straight line. There could be another molecule where the 5 carbon atoms are not in a straight line and they're like this. So these two are two different arrangements of the carbon atoms. Then there's going to be another possibility that 3 carbon atoms in a straight line, and there's so this is how 5 carbon atoms could be arranged. So is the idea clear? Chain isomers.
Yes, sir.
Yes, sir.
So I have a question.
Yes.
Isn't this a structural isomer?
That is part A of a structural isomer. That's the first version.
I thought you're okay. I thought stereoisomer is good. Okay.
We're ignoring stereoisomers right now. We're not doing that right now. I just said that there are two main branches. One is structural, the other one is stereo. We're going to come to stereoisomers later, but right now we're focusing on structural isomers. And that's the first type. That's known as a chain isomer. Now, in this type, it's very important to know, okay, what is not an isomer. Like if I say I have a molecule and the molecule looks like this, it looks probably so it looks let me just make sure. So it looks like this, right? 5 carbon atoms. Do you think I've drawn a different isomer compared to all the other threes? Is this a different
No.
molecule? Or is it the same? I mean, is this a different arrangement compared to the first three? Or is it the same as the first? So you're talking
It's a different one.
It's different. It's different.
Different arrangement.
It looks different, right? But the fact is that these two are exactly the same. I said, remember that when you're drawing when you're writing formulas, these are not the three-dimensional. These are not the three-dimensional shapes of the molecules. These are just showing that which atom is connected to which atom, right? It's not the shape of the molecule. So make sure if the bond is. So I'm going to start with the first one. Like, so 5 carbon atoms in a straight line. If I draw it like this, these two are exactly the same. I mean, there's no difference between them. It's 5 carbon atoms in a straight line. Remember, bending or twisting a molecule will not give you a different molecule. It's going to be the same molecule. It's just a twisted round version of that. Is that clear?
Yes, sir. Yes.
Yes.
For the first one, right? So remember, bending. When I say an isomer, it has to be structurally different. It has to be the atoms got to be arranged in a different way. The bonds, to form an isomer, you would have to break bonds and you would have to rearrange them. Like if you have your hand, to make an isomer of your hand, you would have to break your fingers and you have to connect them in some different arrangement, right? That's the same. That's the same thing that you're going to do with isomers, structural isomers. So bending and rotating something, like if you have a hand and you just draw a bent version of your hand, or your fingers stretched in one direction or open in one direction, that's not an isomer. That's the same hand, right? So bending and rotation is not isomerism. Does not is not. I'm just going to write bent and rotated versions are not isomers. Bent, rotated, twisted. Like if you just twist a molecule around, are not isomers. And this is one of the most important things, because that's where most people make a mistake. They think these two are different, which they are not. They think these two are different. Now look at these two now. They still look different. I mean, they kind of look different, but they're exactly the same. Look at this. That's 1, 2, 3, and 4 carbon atoms. Now I'm going to isolate. I'm going to check the connections. So look at this. There are 4 carbon atoms in a line, right? With 1 carbon atom coming out of that, right? This is exactly the same. It's 4 carbon atoms in a line. And from the second one, there's another carbon atom that's coming out. So do you see the similarity now?
Yes, sir. Yeah.
Yes, sir.
So even though they kind of looked very different, but this one was just a twisted version of the same one. It was exactly the same. In exactly the same way. This is just a twisted version of this one. So you have to be careful about this one, that bent and rotated versions are basically not isomers. You would have to sort of break the bonds, and you would have to sort of rearrange them in some other way. That is going to be some very unique way. So clear at this one, we're going to move on. We'll Hamza, is this there?
So can you show us an example of an actual isomer?
Of a?
An actual isomer.
I mean, these 3 were actual isomers. The first 3.
Oh, okay.
I mean, the first 3 were actual isomers. They were 5 carbon atoms. This is 5 carbon atoms in a completely different arrangement. This is an isomer. I mean, so these 2 are isomers. These 3 are isomers of each other. 4 carbon atoms. So they're, I mean, this thing and this thing have no similarity in arrangement. They're 2 completely different arrangements, and they have the same number of atoms. This and this are basically the same molecule. This and this are basically the same. Is that clear?
Oh, okay. All right. Yes.
So next one, part B is we've got, and this is the second one. The second type of isomers are known as positional isomers. And remember, these are, we're still talking about structural isomers. So what's a positional isomer? That's a subtype. What a positional isomer is, you change the position of a certain group. So if they ask you to draw a positional isomer, simply change the position of a particular group. Any group, if there is a group. So let's say I have an alcohol. And that alcohol has an OH. I'm ignoring all the hydrogens. So there are 5 carbon atoms with an OH at the end. So I can make a lot of positional isomers. Like there could be another molecule which is going to be an isomer, which is going to be structurally different, and that would be that there would be 5 carbon atoms, and I can have the OH on the second carbon atom. Is that clear?
Yes.
Yes, sir.
So that's a positional isomer. This one is pentan 1-ol. This is pentan 2-ol. So the position is changing. Nothing else is changing except for position. So in chain isomers, you change the carbon arrangement. In positional isomers, you pick any group. It could be any group. It could be a double bond. It could be any particular group, and you can start changing its position. How many different isomers, positional isomers, can you make? It's like if you keep the carbon chain straight, you can have OH over here, right? So that's another one. And That's about it. Can I make another positional isomer?
No,
I mean,
then it's the same.
then it's going to be the same twisted, flipped.
Yeah.
For example, if I put the OH over here, then these two would be exactly the same. I mean, this one with this one. They would be exactly the same. I just need to rotate this or flip it around. Like I pick it up and put it the other way around, it looks exactly like this. So these two are just flipped around versions. They're exactly the same. 1, 2, 3, fourth carbon atom, which this one is also 1, 2, 3, fourth carbon atom you got in OH. So that's not an isomer. Right? So is this clear? This one, positional isomers.
Yes, sir.
So then the third one, so the third one is known as a functional group isomer. So what you can also do is you can change the functional group. So remember what was an isomer? An isomer was that you have the same molecular formula but a different structural formula. So you have the same number of atoms but a different arrangement of the atoms. So you're free to arrange them in any different order you like. So you can also change the functional group. I mean, you can change the carbon chain, you can change the position of the groups, and you can change the groups themselves. So for example, we'll start with number 1. Here are some groups that are functional isomers of each other. So alkenes and cyclic alkanes, cycloalkanes. I mean, they are different functional groups, but they're isomers of each other. So as an example, if I have 3 carbon atoms, and this is a propene molecule, and this time I'm going to draw the hydrogens. Let's say these are all hydrogen atoms. And there's a cycloalkane. The 3 carbon atoms are arranged in a cyclic manner. So there's H, 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 and H, and so you've got, if you look at the 2 molecules, one of them is an alkene, and an alkene is C3H6. The other one is an alkane, all single bonds, it's saturated, but it's still C3H6. So that means even though the functional group has changed, this one is an alkane, this one is an alkene, but they are still isomers. They have the same number of atoms, but they're arranged differently. This one, 3 atoms are arranged differently. Is that clear? Yes or no? Is this
Yes.
clear?
Yes, sir.
That's a similar. So you can do a lot of things. You can change the functional group in many ways. Remember carboxylic acids and esters are isomers. So one example is like if I have a 3 carbon atom carboxylic acid and there's double bond O and OH. And here are all your hydrogens. This is C3H6 O2. And there's an ester now. An ester, it's the same kind of functional group, but it's somewhere in the middle of the chain. C double bond O and O. But it's in the middle of the chain. So that's your carbon atoms with hydrogen. So one of them is an ester, but it's still C3H6 and O. O2, sorry. So C3H6O2. So they have the same molecular formula, same number of atoms, but they are arranged differently. One of them is a carboxylic acid. The other one is an ester. And there are others as well. Aldehyde and ketones are basically functional group isomers. Aldehyde and ketones were very similar. In aldehydes, the double bond O was in the middle of the chain. So you had, that's it, sorry, in aldehyde, the double bond O was at the end of the chain. So this is H, there are 2 H's with this one, 3 H's with this one. In a ketone, it's a different functional group, but the C double bond O is in the middle of the chain. So they're 2 different functional groups, but they're isomers of each other. So that's C3H6 and O. This one is C3H6 and O. So they're both isomers of each other. So that's functional group isomers that you can change the functional group. You're free to change the functional group. You have complete freedom to arrange them in any way that's possible, as long as it's a correct structure. So mainly 3 things can be done, and you can do all 3 things together. I mean, you don't need to, the examiner can be very specific. He might ask you for a specific chain isomer. He might ask you for a positional isomer, so change the position of a group, or he might be very specific and ask for a functional group isomer. Is that clear?
Yeah.
Yes, sir.
So
Yes.
you were allowed to remove the double bond in the first one.
You're allowed to do anything as long as the number of atoms are exactly the same.
Oh, okay.
Okay, so it's up to, you can change the way the carbon chain is, that's the chain isomer. You can change the position of the double bond, put it somewhere else, that's a positional isomer, or you can just change everything altogether. That's a functional group isomer. You can just get rid of the double bond. Or if it's a carboxylic acid, you can change it into something else. So I'm going to do an example of an isomer. Remember, as the number of atoms increase, the number of possible isomers, they grow exponentially. So let's say I have C3H6 and O2. There's a molecule and I'm being asked to draw isomers for this. And the first isomer has been drawn for me. It's a carboxylic acid. So hydrogens, so that's C3H6 and O. So first thing, I can't have chain isomers with 3 carbon atoms, because if it's 3 carbon atoms, you can't really alter the carbon chain. So remember, you can't, the minimum carbon atoms that are needed for chain isomers to form, that is 4. Is that clear? You can't rearrange 3 carbon atoms. That's it. For 4, you can rearrange them in this manner. For 3, you can't do that. Like if you have 3 carbon atoms, that's it. You can't do any other arrangement. Is that clear?
Yes.
Yes, sir.
Yeah, I cut out. What are we
Yes,
talking about
sir.
right
Yeah, I was just saying I'm trying to make isomers of this molecule.
now?
Right.
Okay.
So I was just saying that I can't really have chain isomers, right? So first thing, I'm just going to start making any sort of random changes to this molecule, as long as I've got 3 carbons, 6 hydrogens, and 2 oxygens. So what can I do with this molecule? What I can do is I can put the OH group at some other position. So maybe this molecule. So I'm free to remember, think of it as breaking something off somewhere else and putting it somewhere else. That's basically what structural isomers are all about. You're just rearranging things. So I got 3 carbon atoms. I'm going to put the OH over here and keep the double bond in its original position. Now this would have 1H. This will have so I think that's still C3H6 and O. What I did was I put the OH somewhere else. Is this a functional group isomer, or is it what type of isomer is this? These two.
Functional group.
That is a functional group, because you had a carboxylic acid and now you have an aldehyde and you've got an alcohol. If I want to name this molecule, what would that be? What would the prefix be?
Pro.
All.
Pro.
I think it's going to be prop. AN, because there's no double bond between the carbon atoms and it's an aldehyde, so it's going to be al, propanol. And you're going to count from this side. So there's a hydroxy branch at the second one. So it's 2 hydroxy. So it's 2 hydroxypropanol. So anyway, so let's let's make more of this. There could be another positional isomer where I could break the OH from this point, put it on the next carbon atom. That's another isomer. So you're free to do anything. That's going to be what type of isomer am I doing to this one, like relative to this? Like the OH has now been moved to this position. The double bond over there, and these are your hydrogen atoms. So if you compare this with this, what type of isomer did I make? Like in reference to this?
Positional.
That's
Positional.
position, because I changed the position of one of the groups, right? And then I can make another functional group isomer. What I can do is I can, like, if I take this and I can turn it into a function, I can put the double bond over somewhere in the middle. So that would be a ketone now. And keep the OH on one side. So these two are functional group isomers because I changed the double bond over position. So what else can I do? I can do another thing that I can, there's a double bond O over here. What I can do is, instead of the double bond O between the carbon and oxygen, I can put the double bond O double bond between the carbon atoms. Okay, so I'm going to try that one now. So it's 3 carbon atoms and the double bond goes over here. The OH was already attached here and there was an O, but O needs 2 bonds, so I'm going to put an H next to it. The rest are hydrogen atoms, so it's still C3H6O. So what I did was I changed the position of the double bond. Like it was over here, I decided to put it between the carbon atoms. So that's this one. Now this one can have lots of positional isomers. I can change the position of the double bond. It's over here, I can put it over here. And that would give me another positional isomer. So the OH still C3H6O. And then there would be lots of other positional isomers. I can put the OH on this side, put the OH on the other side. So there could be, we can just go on and we can make many isomers. So remember, you can do 3 things. You can either change the functional group, you can either change the position of something, or you can change the carbon branch, which you can't do in this case because the carbon branch is kind of fixed. 3 carbon atoms, you can't do much with that. So is this clear, this thing?
Yes, sir.
Yes, sir.
Yes, sir.
So try drawing. I mean, that's your task for now. Try drawing for ethanoic acid. And make sure, so we see if you could draw 6 isomers for this. Draw 6 isomers. I'm going to send this as an assignment. This is slightly more challenging because it's got fewer atoms, so you would have to really think about this one. But you would have to draw 6 isomers, structural isomers. And each one would be like, it's either going to be a positional or a functional group or a branch isomer. So think you can make a cyclic, so you can do whatever you like, as long as 2 carbons, 4 hydrogens, and 2 oxygens are in the molecule, and as long as it's a proper structure. So you're free to do anything and free to rearrange this. So that's your assignment. I'm going to post it in Google Classroom, okay? 6 isomers.
Okay, sir.
Okay.
Chale. Okay then, everyone.
Sir,
Yes.
sir, can I ask you something?
Yes.
Is it possible for you to send past papers on topics that we haven't covered with you yet?
So we can try energetics, right?
No, like not to go through. As in, my point is, we have end of terms in a while, yeah.
Okay.
So I just wanted to get some practice, and so I was asking, can you send the past papers? for just topics? Like,
For-
are you allowed to do that?
No, for the previous ones or these ones?
No, like I'm studying on my own for the end of term. Yeah.
No, but for the older topics, right? Like energetics and equilibria.
Yeah.
Okay, I'll send those. I'll send those right now.
Yeah, please. Thank you.
Chalo, ठीक है. Okay.
Assalamualaikum, sir.
Allah
All right,
Hafiz.
sir. Allah Hafiz.
Allah Hafiz.